Smart structures are a vast and popular research area. The potential of these structures in aeronautics is very high. But what are these structures exactly? You will probably read as many definitions as there are researchers and engineers working in this field. And I would like to share my view on smart structures, which in my opinion is a general, all-inclusive definition. This definition is based on the structural taxonomy of Professors Wada and Crawley, which they presented in a journal paper in 1990. Later in 1994, Professor Crawley referred to this taxonomy again in another journal paper. And I will share these papers with you for further reading, as well as some other overview papers of smart structures. While reading those papers, you will see that I depart from other, more popular views on smart structures. Let us say that we can represent all existing aeronautical structures in this Venn diagram. Part of these structures are the adaptive structures. These are structures that can change their shape or capabilities based on a certain functional requirement. An ideal example of an adaptive structure is a wing flap. Flaps are extended from the wing to change the camber of the wing, and in most cases also to increase the surface area in order to fulfill an essential functional requirement for an aircraft, namely fly slower during takeoff and landing. Another category of structures are the sensory structures. These are structures that can sense their behavior, which can be static or dynamic. An example of a sensory structure is a wing, which is equipped with strain gauges to measure the strains and deformations of the wing, and an accelerometer to measure wing tip accelerations. When adaptive and sensory structures are combined, we get to the so-called controlled structures. These are structures that can sense certain static or dynamic behavior of the wing, while they can also act on the disturbance which is caused by the static or dynamic measured behavior. A typical example is a gust load, which is a dynamic vertical wind and which causes the wing to move up and down. If you have ever flown in an aircraft, I'm sure that you will have experienced turbulence, which is a kind of a series of gusts. The upward and downward motion of the wing is measured using accelerometers, which give a signal to the aileron of the aircraft to move in a certain fashion, such that the effects of the vertical wind or the gust are mitigated. The final category are the active structures. These are controlled structures where the adaptive and sensory structural parts also carry primary loads. Furthermore, the actuation and sensing capabilities are distributed, so these are typically highly integrated structures. I still did not answer the question what a smart structure exactly is. A structure becomes smart when the relevant functionalities and disciplines are highly integrated. Hence, smart structures are by default multifunctional and multidisciplinary. And this is, in my opinion, the essence of smart structures. So they do not necessarily have to do with fancy configurations or concepts, or with materials that are actuated using electricity or other exotic means. No. Off-the-shelf materials, such as aluminium or carbon fibers, can be used, as well as typical electromechanical or hydraulic actuators. Of course, smart structures can be exotic and out of the box, but they do not necessarily have to. This is a bit in contrast with what you will find generally in literature. Let's now look at what this definition means for our taxonomy. Adaptive structures can be smart. Let us look at our flap example again. A flap typically extends from the trailing edge of a wing, and its sole purpose is to generate sufficient lift for the aircraft to fly at lower speeds. The main loads of the wing are still carried by the wing box. Now imagine that the flap is integrated into the wing box, such that the whole airfoil can deform seamlessly rather than having a flap sticking out at the trailing edge of the wing. This makes the wing itself capable of deforming for the high lift configuration while it carries the main wing loads with that very same structure. And this makes the wing multifunctional and hence a smart structure. The same holds for sensory structures. Again, I'm going to use an example I gave earlier, the strain gauge. Normally, strain gauges are glued onto a surface. Let's look at the wing skin, of which one would like to know the strains under dynamic loads. Now imagine that we could integrate a sensing material into the stacking sequence of a carbon fiber skin. Then the skin material would be able to carry the loads of the wing, while it would be capable of measuring its strain at the same time. Again, we have a multifunctional structure, a material in this case, which we can call SMART. If we combine an adaptive structure with a sensory structure, where at least one of them is smart, we have a smart controlled structure. The control itself can also be smart, but this is a typical control theory aspect which would lead us too far from the topic of the course. And finally, the active structure is by definition already a smart structure. A structure does not have to be entirely smart to be called a smart structure. Only a few parts of the structure can be smart. Therefore, we can distinguish two main categories of smart structures: the fully integrated smart structures or the bolt-on smart structures. I guess that the first category speaks for itself, while the second category means that smart structures are bolted onto conventional structures or even other smart structures. Yuri will provide us with an excellent example at the end of this module, the smart chevron. Just to lift the veil a bit, the smart chevron is bolted onto the back of the engine nacelle and exhaust nozzle, which each are just conventional structures. However, the overall nacelle nozzle chevron combination is again smart, since this combination does not only bypass cold air around the hot internal part of the engine, it is also able to reduce the jet noise.